Hello students, welcome to PG Pathshala. I am Dr. Dinesh Kalyanasundaram from IIT Delhi. Today we are going to discuss about a module, Fourier transforms. To understand the Fourier transform, its properties and the practical application, these three are going to be the objectives of today's lecture. What is Fourier transform? We earlier saw Laplace transform. Then why do we need Fourier transform? Those are the key questions what we are going to solve today. A Fourier transform, as you know, a word transform itself means it is going from one space to another space. That space, one can be a time space and one can be a frequency space. And why do we need transforms? Well, we need to solve a few things. We need to find a solution, and that's why we need a transform to come to a useful and quick solution. When we have already a Fourier series, then why do we need Fourier transform? Are these two series connected? Are these two properties connected? We are going to see what is the relationship. Okay. While a Fourier series is useful for periodic functions, the Fourier transform is used for non-periodic functions. That is the key difference. So you can take any function, and if the function is going to be periodic, then you can write down as a series solution. So that is a Fourier series, and then you can find out A naught, B naught, A1, A2, A3, and B1, B2, B3, like we did in the previous lecture. Now, are there any functions which will not be periodic? Yes, in real life there are many functions which will not be periodic. So that time, how do we solve that? We can't use Fourier series. So that time we end up going to another form, which is now called the Fourier transform, and we are going to see how it can actually be useful. So Laplace transform and Fourier transform are the only two mostly used transforms in nearly everywhere, and Fourier transform is actually the most useful transform. When we talk about material science, when we talk about biology, when we want to find out what is there and what is not there, what is the characteristics of a function, everything is going to be just Fourier transform. Now, we need to understand what is a Fourier transform, what it can do. Okay. Most of the time, what we get is a signal in a time domain, which means we will see a pattern with respect to some time, right? That is the only thing we can record. Now, when we record with respect to time domain, we don't know how it is characteristics of anything. So we have to look it up from a different angle. Now that different angle is a frequency, and that frequency, for some reason of physics, it has become a relation or there is it is a characteristic property of a material. So the moment the frequency is a characteristic material of a material, then we can actually connect it, and then we can relate once we come into the frequency domain. So that is why we are taking a Fourier transform. So Fourier transform essentially converts any signal that a detector is detecting in time domain to frequency domain. Then we can do always an inverse transform to come back to the time domain, and this is always the energy is kind of conserved. So there is always a 1:1 relationship between any particular function of when we convert it by Fourier transform and take an inverse, there is always a 1:1. So in that way, there is no false signaling which will happen. Let us define Fourier transform mathematically. What is a Fourier transform? It will become an infinite weighted sum of an infinite number of sinusoids. Okay, because this is the only way we can capture or we can replicate a completely random signal, any random signal. So we are going to see how a square signal can be represented by sum of sinusoids, and we have already done that in the Fourier series also. And similar functions we are going to see how a triangle can be represented. And here, so if f of t is a function, then its Fourier transform, mathematical definition, is going to be the Fourier transform will always be represented by a capital F. Okay, let us assume the function is a small f of t. So the capital F of small f of t will be integrated between minus infinity to plus infinity. Okay, the function will be multiplied by e power minus I omega t, and it will be integrated with respect to dt. Then once we get that value will be called as f of omega. Omega is the frequency. Initially we had f of t, that will be the function in time domain. Now what is e power minus I omega t? E power I minus omega t is nothing but cos t plus I sin t. I is representing the imaginary value root of minus 1. Now what is the key thing that we learnt in doing Laplace transform? Whenever we multiply by e power minus omega t or e power minus something, it's a exponentially decaying function. So when you multiply and then integrate, this multiplication by e power minus omega t or e power minus any function t or any variable t, and then integrating, it is able to actually capture all the energy related with the function f of t, and that is the beauty of it. This is something which you should not forget. So then once you take an integral like that, you don't really have to go up to infinity, but here we are going to apply the limits as infinity and minus infinity. And then when you solve, you will get the Fourier transform. Now after you get the Fourier transform, you can add different signals. Let's say you get 3-4 signals from different detectors, then you can do a multiplication or addition depending on what you want to do with the signals. Then you want to again find the inverse, right? So you want to find go back to the same original function so that you know that what you have done is right. Then the small f of t will be equal to 1 over 2 pi minus infinity to infinity f of omega times e power I omega t d omega. So this is only the inverse to come back to the function. Okay. So the transform can be represented f of t. So small f of t going to capital F of omega will be called as f, will be denoted by capital F. And when it is the inverse from capital F of omega to small f of t, then we will just say capital F inverse minus 1 to the power of minus 1. Fourier transform. We want to know where Fourier transform can exist. Only condition, and it's the most sufficient condition, that f of t should be absolutely integrable. That is, integral minus infinity to infinity modulus of f of t dt should be less than infinity. This is the condition for existence of Fourier transform, which means when you integrate between limits between anywhere to anywhere and integrate it over time dt, the value should not reach infinity. It should be some sizable number. We want to understand the difference between Fourier series and Fourier transform. So we are going to very minute steps to understand the difference. Let us take a function f of t is cos t. Now case 1, if you write the Fourier series, f of t is equal to a naught by 2 plus sigma n is equal to 1 up to infinity times a n cos 2 pi n t by t. plus bn sine 2 pi nt by capital T full brackets. Now for this function we need to find a0, an and bn. Then once you do the whole series, now f of t is equal to cos t. So if you put cos t is equal to a0 by 2 plus the whole right hand side, then you can find a0 is equal to 0, b0 is equal to 0, then an is equal to 0 for n not equal to 1, and a1 is equal to 1, that is an. Then you can write the cos t is equal to the same thing. When you substitute, you will find out it is the same cos t. That means there is only one frequency at omega is equal to 1. We will see the same function. What will happen if we are, by definition, Fourier transform of any function small f will be equal to minus integral to minus infinity to plus infinity f of t e power minus I omega t dt. So instead of f of t, we are supposed to substitute cos t, because that is a function cos t. So once you substitute cos t, then you can write cos t as a sum of e power it plus e power minus it by 2. It's an average of the two exponential functions. Then you can take a sum of two integrals. You can divide the whole thing as one integral into two equal integrals, not equal but two separate integrals. Then you can solve it. Then once you take an integral, you will get the function direct delta omega minus 1 plus direct delta omega plus 1. So if you do an integration of e power minus I omega or omega minus 1 of t dt, then this is the solution. What is a direct delta function? That is very key that we need to understand. A direct delta function is like a very sharp, thin peak. The function will be 0 everywhere else. That is a direct delta function. Now when it says direct delta omega minus 1, that means it is when omega is equal to 1, then the function delta, then there is a sharp peak and the value is 1. When it is direct delta omega plus 1, then omega plus 1 is equal to 0. If we substitute, then omega should be minus 1, and that is when you will have the second frequency. Here when we do Fourier transform of the same function, here we are getting two values of frequency at omega is equal to 1 and omega is equal to minus 1. But since frequency cannot be negative, so effectively it is only one frequency, that is omega is equal to 1. Fourier series versus Fourier transform. Let us see another example too. Let us assume there is a square wave which is repeating as shown in the figure. Now Fourier series for the square function, so you take a f of t, then you calculate the Cn, where Cn will be equal to 1 by t, which is the time period, minus t by 2 to t by 2, f of t e power minus j omega naught nt dt. Then when you solve the function, because it is the value of f of t is just going to be 1, then you will get Cn will be equal to 2 by t sine omega naught n t1 divided by omega naught n, where omega naught will be equal to 2 pi f naught or 2 pi by t. Now let us plot this value of Cn to see the frequency spectrum. Let us see few cases how we can solve this value of Cn. Let us plot it on the graph as shown in the right hand side. Then Cn we can plot it for a time period t is equal to 4 and t1 is equal to 1. Then Cn will be equal to 1 over pi n sine pi n by 2. Plot, we will get something which is shown as in the right hand side. You can see there are frequencies which are coming on the positive side as well as on the negative side. Now there can also be an amplitude in the positive direction as well as in the negative direction. Let us see another case of solving the same problem. We can assume the total time period is 8 and t1 is equal to 2. Then when you solve it, you will see the number of lines or the frequency or the solutions are increasing, and you can see the distance between consecutive frequency plots f0 in the frequency is like decreasing. And again we are going to have both right side and left side, that means negative frequency and positive frequency, and of course negative frequency does not exist, and we will have some values Cn with the negative amplitude for some of the frequencies. For time period of 16 and t1 is equal to 4, let us see a few cases. And in this third case, we can see the number of solutions are increasing, the frequencies are increasing as shown in the. Let us assume the time period t, which is equal to 16 in the previous slide, now tends to infinity. Then the frequency will tend to 0. That is, frequency will not repeat itself, and function or signal becomes aperiodic or non-periodic. So for this aperiodic function, Fourier series does not exist. So we go for Fourier transform for the function f of, that is capital F of t, capital F of small f of t, integrated between minus infinity to infinity f of t e power minus I omega t dt. That we will hereafter call it as capital F of omega. Fourier series and Fourier transform. Now we have seen a lot of examples and case studies, and let us summarize what is the difference between Fourier series and Fourier transform. Fourier series, it's a relatively longer process to determine the coefficients a1, a2, a3, b1, b2, b3 and the frequency. Fourier transform, it directly gives you the frequency information. Fourier series. Fourier series is applicable only to periodic functions. Fourier transform is applicable to both periodic and non-periodic functions. That is the second difference. Then in Fourier series, shows frequency in discrete form, which means it will just give you some exact values. Fourier transform, it shows frequency in a continuous form. Those are the three key examples. Let us see some examples, that is Fourier transform of some very important function. Example 1, Fourier transform of e power I omega naught t. So when we, as you can see from the graph, there is a real part which will follow cos omega t, cos omega naught t, and there is an imaginary part which will follow sin omega t, omega naught t. So when we solve the function f of e power I omega naught t, then we know we have to integrate it after multiplying it by e power minus I omega t dt minus infinity to infinity. If you remember the Fourier transform, whenever we multiply something e to the power of minus omega or any function t, it has a special property of decreasing exponentially, but it will, when you integrate it, it will try to absorb the whole energy into the integral. So in that way, we need to only do it for a few steps, but the whole message or the energy or whatever is getting conveyed will be conveyed when we are multiplying with e power minus omega something and then integrating it. So that is the same thing we are doing here. So when you multiply with the function I omega naught t, then you can see f of omega will be equal to 2 pi delta omega minus omega naught. What does that mean? At omega is equal to omega naught. The amplitude is 2 pi. Anything which is the value before delta will become the amplitude of the function. Function I omega naught t is an essential component in the Fourier analysis, and it is a pure frequency. We are going to see example 2, where we have to find the Fourier transform of cos omega naught of t. What is cos omega naught of t? First we will plot cos omega naught t, that is as shown in the left hand side image. The blue curve follows the cos omega naught t. Then let us put it in the equation. Cos of omega naught t will, f of cos of omega naught t will be equal to minus infinity to infinity integration acting upon cos omega naught t into e power minus I omega t dt. What you will have to remember is, if the function comes with omega naught t, you probably want to maintain it as omega naught t. You shouldn't change between omega and omega naught frequently, because then it will lead to confusion. We will clarify those examples later, but let us see how to solve this one now. Cos omega naught t can be written as e power I omega naught t plus e power minus I omega naught t average. So that is what we have written. Then you can divide them again into two different functions, as we saw in a previous example. Then when you solve this, you will get pi times delta omega minus omega naught plus pi times delta omega plus omega naught. So what does that mean? Frequencies are at omega naught, that is omega is equal to omega naught, and the frequency are at omega is equal to minus omega naught. So there we will get the frequency. And what is the amplitude of the frequency? That is going to be pi, because that is the coefficient in front of delta, and that is what we are going to get. We are going to see example 3 and another example 4. Fourier transform of delta of t and just a constant function 1. So the first one is delta of t. What is delta of t? Delta of t, or direct delta of t, is a sharp function which is existing only at one point, and its value is 0 in others. When you take a Fourier transform, since it has no imaginary part will be 0, and the real part is going to be just 1. When you take a function, a constant function, or a function, here we have assumed the constant is 1, when we take the Fourier transform, then it will just simply be 2 pi delta of omega, and that is shown in the right hand side figure. Again the imaginary part will be 0, real part will be 2 pi. We are going to see the Fourier transform of a rectangular. This is a similar function which we saw previously, and here we are going to assume that t1 is equal to 1 by 2, and that's why you see the square box is between minus 1 by 2 to plus 1 by 2. We know the solution. The solution will be a continuous function, and the imaginary part will be 0. This is what we saw earlier. If you put the value or in the equation, then f of omega will be equal to integrating between minus 1 by 2 to plus 1 by 2 f of t e power minus I omega t dt. Then when you solve it, you will get finally sine of omega by 2 divided by omega by 2. So I would encourage students to go through the steps and try to derive it on your own, so that you will get familiarized by how to do integration in all the other modules. So if you write the function, then the Fourier transform will be equal to sine c omega by 2. Sine c is Sin x by x is always known as sin c. Let us see another example, triangular function. So the triangular function instead of the square is going to just have a triangle with a sharp point at value of 1. Now when you take the Fourier transform, it is going to be similar. It's always going to be the frequency, the real part is going to be on the upper side. And the solution is sin c squared x, which is sin squared x by x squared. Let us see how we can play around with this Fourier transforms. Earlier we saw how we can get square waves and stuff by just using just sinusoidal but different frequencies and different amplitudes. So you can see the right two top images where the frequency is different. So one is a frequency f and another is a frequency 3f. And the frequency 3f also the amplitude has come down, assuming that is like 1/3 of the frequency or amplitude of the center graph. When you combine, you will get a graph which is as shown in the left hand side. Now when you take a Fourier transform of this function, sin 2 pi f of ft plus 1/3 sin 2 pi 3ft. So when you take Fourier transform, you will find out the solutions are f and 3f, and they will have different heights because the amplitudes are different. Let us see how to describe a square target signal in terms of sinusoidal waves. This is something that we have done before also. So as you can see, let us start with a frequency f and add it to a frequency 3f. And amplitude of the 3f frequency is 1/3 of the first frequency. Then when you add it, you will get the one which is on the bottom of the slide. Now here is the point. You have to take an Excel sheet and do it by yourself. Then you will probably understand what we are trying to do. What we have done is we have added more sinusoids to the previous slides. Okay, so probably we have added 1/5 over sine 5 times of omega t. Then we will get what is shown in the bottom of the slide. Again, what we have done is we have added more sinusoids, but of higher frequency and smaller magnitude. As the frequency goes up, please remember the amplitude has to go down if you want to describe very fine features. We do the same thing with adding much higher frequency and much lower amplitude. Let us try to solve the square pulse signal with respect to the Fourier transform. Then when you solve it, you can actually see there is a various frequencies, okay, and it is decreasing in amplitude if you solve the square signal. And this is the same thing that we have obtained in the previous slides. What we were trying to do is we were artistically describing the square wave in terms of small sinusoids and trying to capture the same figure using sinusoids of different frequencies and different amplitudes. Now what Fourier transform can give you is, it can give you straight away the same thing, what all frequencies should be used and what should be the amplitude. So that is the usefulness of Fourier transform. Let us see Fourier transform and convolution. So g of t, if it is written as convolution of f of t into h of t, then the Fourier transform of g of t, that is represented as capital G of omega. Then capital G of omega will be just multiplication of capital F of omega and h of omega. So what we are trying to say is a convolution in time domain will be a multiplication in frequency domain. The derivation is given here and you can refer to it. These are some things which are properties of Fourier transform, but it's for a basic understanding. These are something which will be used heavily in the instruments when they are doing, and many of you will be using some form of spectroscopy where a Fourier transform is going to help you get the signal, and that is FTIR, Fourier transform infrared spectroscopy. Those examples and applications we will see in the next slides. Fourier transform and convolution. Continuing from the previous slide, anything that is a convolution in time domain will become a multiplication in frequency domain, and a convolution in frequency domain will become a multiplication in time domain. And that's what the first two equations of in the slide mean. So suppose we want to find g of t, we can always find the small g of t. Suppose we know h of t and f of t. We can take Fourier transforms, so then we will get capital F of omega and h of omega. All you have to do is multiply that. Then we can find capital G of omega. Then what we have to do is take a inverse Fourier transform. So we can always find the unknown by doing Fourier transforms and inverse Fourier transforms and some multiplications. Properties of Fourier transform. So we are going to see the relationship between the time domain and the frequency domain. So the key lesson that we have to learn is how they are related rather than the mathematics. I think if you understand the philosophy, I think it will be more useful and helpful. So linearity is anything which is multiplied linearly. Will the constant c1 and c2 multiplied and added to two functions f of t and g of t. It will remain the same, just it will be multiplied to the Fourier transform f of omega and g of omega with c1 and c2 respectively. Scaling. Scaling is you are increasing the time or decreasing. So f of a of t will be equal to 1 over modulus of a f of omega by a. Shifting in time domain, that means we are going to shift the time t by t naught. So that is t minus t naught. Then in frequency domain it is affecting. Then similarly a frequency shifting will also affect f of the function, the f of small f of t. Then convolution, we saw convolution will be represented as a multiplication in the frequency domain. Then duality. Then differentiation. You can see the differentiation as given below. Practical application of Fourier transform. Fourier transform infrared spectroscopy is the biggest application of Fourier transforms. What do they do? As I told you several times, again they will take any sample and the material, it's a property of the material that a particular frequency is associated with it. So what can we do? We can do material analysis, right? We can do both qualitative and quantitative. Depending on the detector, how accurately can it capture the infrared spectrum. So what do they do? The infrared spectrum represents a fingerprint of a sample with particular absorption peaks. Okay. The absorption corresponds to a particular frequency of vibrations between the bonds of the atom making up the material. Okay. No two compounds produce the same exact infrared spectrum. Then the size of the peaks in the spectrum is a direct indication of the amount of material present. Let us see some practical application of Fourier transform. So as we discussed before, the Fourier transform infrared spectroscopy uses Fourier transform analysis. So let us first see how the system is. We have a source, we have an interferometer, then we send the signal, hits the sample, and there is some signal which gets emitted from the sample and it goes to the detector. So if you see in the middle, the signal coming from the detector kind of a sinusoidal function varying amplitudes and varying frequencies. Looks like it's a mixture. Now we don't know what is the absorbed frequency, because every material has a specific frequency of absorption. Now we apply a Fourier transform. Now what it does is it changes the simple sinusoidal confused wave into a linear spectrum of wave. It is still hazy and confused, but it is going to appear for a particular wave number. That means it is going to be a property of the material. So if a particular wave number appears, then for a particular material, then you know whether that material is present or not, and with the amplitude you can relatively judge how much it is present. So the wave number has a relationship to the frequency, which I will let you to find out, because if I say everything then it's not going to be greatly useful. So you'll have to find out what is the relationship. So in this way, any Fourier transform spectroscopy, so any signal which is going to come, we can actually do some mathematics, especially Fourier transforms, and then find out what is the material in it. And it is the most extensively used technique in material science, in biology, in nearly every field. Students, let us summarize what we have learned in this module. So we have learned about Fourier transform, how it is done, and actually you will need to go and start working on examples. That is the best way to understand Fourier transform or any mathematical modules, because in 30 minutes videos we can only give certain things which are not covered in the book, and you will have to go take examples and do some multiplication, integration, and then find out how you are good at doing. Okay, so in this video we have only covered what is not mostly given in a book for understanding. The goal of this video has been only to apprise you of what and how a transform can be done, but not the integral details. Okay, so you'll have to go and kind of work on it. Okay, so the summary is the Fourier transform is a very useful tool for handling function which contains information in frequency domain. Then it can handle both periodic and aperiodic functions. Okay, then it is the easiest way to get the frequency spectrum of any signal. It can show a continuous change in the frequency, and this is the way that Fourier transform is very useful. Okay, I hope you have enjoyed the video, and please work on the examples by writing down and then looking at the references that is given in the modules. Thank you.